a great pleasure to be back at Harvard at this interesting meeting. The famous singularity theorems of Hawking and Penrose proved the existence of singularities, but didn't say anything about event horizons. And that led Penrose back in 1969 to suggest that perhaps there was a cosmic censor that clothed all singularities behind an event horizon so that they wouldn't be naked, they wouldn't be visible to distant observers. So very roughly, cosmic censorship is the statement that generic smooth initial data cannot evolve to regions of arbitrarily large curvature that are visible to distant observers. Now initially, I think most people hoped that this was true, so that general relativity would be sufficient to evolve everything that happens outside black holes. But nowadays, many of us hope this is false, because it opens up the possibility that we might directly observe effects of quantum gravity. Now, the problem of most interest is, of course, the one in 4 dimensions with asymptotically flat boundary conditions. But that's a very hard problem. There are still many people thinking about it, mostly mathematicians these days. But it's a hard, open problem in general relativity. So people have started to think about this question in other dimensions with other boundary conditions. Motivated by string theory, people thought about what happens to cosmic censorship in more than 4 space-time dimensions. And it was noticed, well, more than 20 years ago, that many higher dimensional black holes are unstable. And then it was shown more recently that the outcome of that instability is that the horizon actually pinches off, forming a classical singularity. So in more than 4 dimensions, cosmic censorship fails. But this pinch-off is supposed to sort of happen at one point in the horizon. It involves probably a very tiny amount of mass. And when quantum effects are included, I think it's pretty clear that what's going to happen is the horizon will simply split, and the black hole will change the topology of the horizon or perhaps bifurcate. And physically, that's what the effect is. And that's what, well, probably what goes on. In this talk, I'm going to stick to 4 space-time dimensions, but consider gravity with a negative cosmological constant. And we'll find some more serious counterexamples to cosmic censorship. As you know, the main motivation for studying gravity with negative cosmological constant is this famous gauge gravity duality, or holography, in which we believe quantum gravity with this boundary condition can be completely described by a non-gravitational quantum field theory living essentially on the boundary of space-time. Well, this negative cosmological constant effectively puts gravity in a box. The conformal boundary at infinity becomes time-like, and you have to specify boundary conditions for the metric and other fields at infinity. So the first counterexample I'm going to describe is in Einstein-Maxwell theory. So we're just going to add a Maxwell field and, of course, a negative cosmological constant. And the boundary condition for the metric is going to be just the trivial 3-dimensional Minkowski space. So we're going to require at infinity the space-time is flat. And the boundary condition for the vector potential is that it will have only a time component, and the vector potential will be static and axisymmetric, but depend on r, depend on this radial coordinate on the boundary, so it'll fall off. It's some sort of localized chemical potential, if you wish. And we're going to study 0 temperature solutions to this problem. Of course, simple solutions are known. If mu is 0, then there's no Maxwell field, and you just get the usual anti-de Sitter space. And also, if mu is constant, there is an analog of the usual Reisner-Nordstrom metric. In anti-de Sitter space, black holes don't have to be spherical. There are simple black hole solutions which are planar, where the horizon geometry is flat, or even hyperbolic. So if mu is constant and not 0, the solution would be this planar analog of the Reisner-Nordstrom solution. But we're going to require that mu is non-zero, but go to 0 at infinity at large r. And so these will be new solutions that we'll construct numerically. And this problem was first looked at 3 years ago or so for totally different reasons, having nothing to do with cosmic censorship. So let's consider the following profiles. Mu will have some amplitude a, and then fall off at some rate, like 1 over r to the n. And we'll consider various n's just to see if it makes a difference. Physically, what these solutions represent are static, self-gravitating electric fields. You just have some electric field which is self-gravitating in this universe with a negative cosmological constant. So we constructed the solutions numerically and found that they only exist, smooth solutions only exist up to a certain critical value of this amplitude, which depends on your fall-off. So here's the results for n from 1 up to 8. And you see it just some number, finite number, which increases with the fall-off. And if it falls off faster than 1 over r, these solutions all approach standard anti-de Sitter space in the interior if you go far inside. Okay, so now here's our proposed counterexample. We take our boundary value of the vector potential to be of that form, but now let this amplitude be time dependent. We'll start with a equal to 0. So in the past, we just have ordinary anti-de Sitter space, and then slowly increase it to a final value bigger than this maximum value. So if you slowly increase it adiabatically, you would think the bulk solutions would stay close to the static solutions we find, but when you get past A max, there is no smooth static solution for it to settle down to, and so we argued a couple years ago that the space-time must just continue to evolve and produce a larger and larger curvature. And then a year ago, George Santos and his student Toby Crisford actually did the full time-dependent evolution and confirmed this. So let me just tell you a little bit about what they found. They considered the n equals 1 profile. So this was a boundary chemical potential or Maxwell field, which went like 1 over r at infinity. Okay, so what I have here is just a quick sketch of anti-de Sitter space. So you think of anti-de Sitter space as gravity inside a box. This is the boundary. This is a horizon. They evolve along ingoing null surfaces. So v equals 0 is this ingoing null surface. Below that, a is 0. This is just pure anti-de Sitter space. And then they turn on the Maxwell field, and they solve it in this upper triangle here. Since they were doing things numerically, they didn't have to turn on the Maxwell field slowly. Here's a plot. They just chose the amplitude A to be 0 for this. Well, this is time on the boundary, which was negative. And then starting at 0, they very rapidly increased it to a value bigger than A max. Okay, so to show you the results, I'm going to focus on one quantity, which is just the square of the Maxwell field. That's basically the square of the electric field as a function of time. We're going to evaluate it on the horizon and on the axis. So these solutions are axisymmetric. We'll just look at it on the axis to see what happens. And this is what they find. Okay, so here's the square of the Maxwell field as a function of time. And the different curves just correspond to different final values of this amplitude A. And I remind you that the maximum that we've had for smooth, non-singular static solutions was 0.678. So these lower values are less than the maximum. And what happens is that the electric field grows and then settles down. These dashed curves are, in fact, the static values for those values of the amplitude. And this one you can see is clearly approaching the static solution. This one is still far from it, but they've since evolved. This was a plot in their paper. They've since gone to much later time, and you can clearly see this approaching the static solution as well. So if your final amplitude is less than the maximum, the time-dependent solutions just settle down to the static solutions as you expect. But if the amplitude is bigger than the maximum, the electric field just keeps growing. And it appears to grow like the square root of time. It's a power law. So, well, since the electric field is blowing up, the curvature is blowing up as well. And the blow up is not just on the axis, which is what I was showing you before, but in fact it becomes large all along the horizon. Now the singularity does not form in finite time. These solutions have curvature which just grows apparently indefinitely. But it does, I would say, clearly violate the spirit of cosmic censorship. You're getting arbitrarily large curvature that's visible to distant observers. And I would argue that this violation is much stronger than what's already been known in more than 4 dimensions, which, as I said, involves pinch-off of horizons and happens in a very small region of space-time. Okay, well, now let me switch gears for a moment and mention a seemingly completely unrelated conjecture. This is known as the weak gravity conjecture, proposed, I guess, here at Harvard over 10 years ago. And these people suggested that any consistent quantum theory of gravity must include charged particles with the ratio of the charge to mass bigger than 1. So if particles obey this, then of course the electrostatic force between 2 such particles will be stronger than the gravitational force, and that's the origin of the name weak gravity. Gravity is weaker than the other forces. Now they gave various arguments in this paper why they believe that would be true. I didn't find them very convincing, but it did start a lot of interest in whether this was in fact true. And one of the things they point out is that, or one of the motivations, I guess, was that if you have particles with charge to mass ratio bigger than 1, extremal charged black holes would not be stable, but they would in fact decay by emitting charged particles. Even though the Hawking temperature is 0, you can pair-create particles in the strong electric field outside the horizon. So a couple years ago, after we had this proposal for a counterexample to cosmic censorship, Kerman Vaffa came to Santa Barbara, and I was telling him about it. And he said, well, I wonder if weak gravity conjecture will save cosmic censorship. And his idea was that in our examples, we have electric fields that are becoming arbitrarily large. If you do have charged particles in your theory, they will be pair-created in the strong electric fields. And the back reaction of many, many charged particles being created could be to dampen out or certainly suppress the electric field, and maybe the curvature would never get very big. Well, I thought that was an interesting suggestion, but it also sounded like a really hard problem, because it sounded like you had to do a quantum field theory calculation in this evolving time-dependent background and then somehow back-react the stress tensor of the created particles, and it became a very complicated problem. But then, just about a year ago, we realized that we can test this using a classical charged unmassive scalar field. Because if you add a charged scalar field, even classically, to our theory, it's possible that the original Einstein-Maxwell solutions would become unstable to turning on the scalar field. This was actually what happened in something called a holographic superconductor, where we found gravitational analogs of superconductors in this context of holography. So there was a suggestion that our solutions could actually be unstable, and the real solutions, the stable solutions, would have a non-zero scalar field. And if that happened, well, then we had new questions. I mean, with the scalar field non-zero, is there still a maximum for the amplitude, or could you find smooth solutions no matter what you do at infinity? And if, in fact, you do find solutions for any amplitude, so you don't violate cosmic censorship, that presumably will only happen if the charge is big enough, because clearly if the charge goes to 0, it'll be unaffected by the electric field, and our solutions would be stable. So we had these questions to check about what happens to our solutions in the presence of a charged scalar field. And so so we looked into it, and let me now just describe what's going on in this complicated graph here. So on the vertical axis, I'm plotting the charge of the scalar field. I'm fixing the mass. So let's just assume we fix the mass for the scalar field, and we're going to vary the charge. And so I'm plotting the charge on the vertical axis versus the amplitude on the boundary. So increasing the amplitude increases the electric field in in our bulk solution. And what the curves represent is the charge you need to get a zero mode. This is the boundary between when our solution is going unstable. So the idea is that our Einstein-Maxwell solutions are unstable if the charge is above the curve, and stable if the charge is below the curve. And these different curves just represent different profiles for our vector potential at infinity, going from 2 up to 10 as you go out. Okay, so let's just focus on 1 to see what's going on. Let's take this top one over here, falling off like 1 over r to the 10th. Clearly, the curves are decreasing simply because as you increase the amplitude, the electric fields are getting stronger. You need a smaller charge to set them unstable. So that's this decrease. These curves all end at the maximum amplitude that we have for a smooth solution in the bulk. So these curves all end at A max. And the line here, okay, I've normalized the charge according to the charge you predict for the weak gravity bound. And the fact that these lines all go below this black dashed line means that if you start at A equal to 0 and your charge obeys this weak gravity conjecture, as you increase it, you will always find your solution going unstable before you reach the maximum amplitude. Okay, so this meant that at the very least, our previous counterexamples were thrown into question if you satisfy the weak gravity conjecture. So then we actually constructed the solutions with non-zero scalar field that exist here and studied their properties. And what we find is that with the non-zero scalar field, there's no maximum amplitude. You can find smooth solutions for any amplitude you want. So you don't violate cosmic censorship. And therefore, the weak gravity conjecture actually saves cosmic censorship, at least prevents this class of counterexamples. So then we said, okay, well, what's the minimum charge you need to save cosmic censorship? And according to this plot, well, it looked like we could actually do with a little bit lower charge. These curves all go a little bit below the weak gravity bound. So we thought, well, that's pretty good. You know, we didn't have any reason to expect weak gravity would get it exactly right. We thought maybe we could lower it a bit. But then we looked at it in more detail and found that no, even with the, okay, so what are we doing? We're taking the scalar field, lowering the charge. The solutions with the scalar field became singular if the charge became too low. So the curve on the right is just a blow up of the curve on the left. Again, charge as a function of amplitude. This is the region where the scalar field is non-zero. And what you see, quite remarkably, is that the scalar field develops singularities if you're below this weak gravity bound. So you can violate cosmic censorship in this region. Increasing the amplitude makes it singular. So it appears that the weak gravity conjecture is both necessary and sufficient to avoid this class of counterexamples to cosmic censorship. All right, that's where things stood about 6 months ago in the fall. And then we started to think about vacuum counterexamples to cosmic censorship. And so this is work that's still in progress, but let me just tell you the idea. Now we're throwing away the Maxwell field, throw away the matter, and all we have is vacuum, and we're going to put a metric on the boundary which has this differential rotation. So it takes this form where omega is going to again have an overall amplitude, a profile where p goes to 0 as r goes to infinity. And we construct stationary solutions of Einstein's equation with this boundary metric and find that, again, there's a maximum amplitude beyond which smooth solutions don't exist. Well, now we can try to violate cosmic censorship. Let the amplitude be time-dependent and grow from 0 up to some maximum bigger than A max. Will cosmic censorship again be violated? Well, there is a slight complication, because before we get to A max, the solutions develop an ergo region at some amplitude A ergo. Okay. And remember, an ergo region is simply a place where your time translation killing field turns over and becomes space-like. And as we just heard in the talk, it was perfect timing, in the previous talk, it was explained that when you have this ergo region around usually a rotating black hole, you have superradiant scattering. You can send in a wave and have it reflect with bigger amplitude. Now in anti-de Sitter space, that leads to the possibility that you would have an instability. Thank you, I'll finish up in just another minute. So that may cause an instability due to superradiant scattering of these non-axisymmetric modes. Okay, well, time-dependent evolutions are underway, and what we find is that the curvature is indeed growing as a power law, just like before. So we don't seem to see any complications associated with the superradiant scattering, and the weak gravity conjecture can't save you this time because there's no electric fields. Charged particles won't have anything to do with this, although I was talking with Kerman yesterday, and he had some ideas on a modified weak gravity conjecture involving high spin fields that might, anyway, something for the future. Okay, quick word about black holes. Everything I've told you about so far is for the zero temperature case, but we can look at solutions with actual black hole horizons. In the electromagnetic case that we looked at first, you don't violate cosmic censorship at non-zero temperature. The solutions continue to exist. But for the vacuum case, you do. So smooth solutions at finite temperature with horizons only exist up to a maximum amplitude. And as you increase the temperature, the difference between the maximum you can reach and the ergo region actually goes to zero. So if you had a planar black hole and you increase this rotation, there's no stationary final state. And so we think the curvature will again grow and will violate cosmic censorship. And so let me just summarize. I've shown you that we can violate cosmic censorship with just a Maxwell field in 4 dimensions. Adding a charged scalar field with sufficient charge removes this violation. The bound on the charge is precisely the weak gravity bound in ADS. And finally, there appear to be violations analogous to what we saw with the Maxwell field in pure vacuum. Thank you very much.
Dan?
Hey, yeah, thanks, Gary. That was very interesting. Maybe just a comment. So at least for me, the way I think about the weak gravity conjecture is that the reason we need these charged particles is so that we can cut electromagnetic Wilson lines. And so for gravity, there's actually an analogous thing. So there are also gravitational Wilson lines that we would need to cut. And what you need are things which are charged under gravity.
Just massive particles.
Which is just anything. And in particular, I think it includes gravitons. So I guess that would make me suspect that maybe there's something special about the spherical symmetry here and that it's preventing gravitons. Is that right? Or is it, are there, I wasn't totally sure because you are assuming some kind of rotational invariance, right?
Okay.
So, but is it enough to rule out gravitons or not?
No. Okay. So you're right that the metric I showed you on the boundary is axisymmetric.
Yeah.
And so the solutions that we construct that we look at first are axisymmetric as well as stationary.
Yeah.
Okay. That doesn't rule out gravitons. There's m equals 0 modes, which are axisymmetric, and there's still plenty of gravitons. But we've also looked, when we're doing the evolutions, we've looked at cases where there's no symmetry at all.
Okay, yeah.
So we can take some initial, and we see the same thing. So,
how do you do that? You do that numerically?
It's all numerical, yes.
Oh, I see, okay.
Yeah.
So, and you would say also then in the ENM case, because you said generic initial data in the beginning, right?
That's right.
So that's...
So generic means that, yes, you can put in initial data with no symmetries, and you get this behavior. Evolved numerically.
But you had this comment about an instability with the ergosphere, right? I guess that... shouldn't the generic initial data turn that on?
Okay, so my comment about the instability in the ergo region was for this class of stationary axisymmetric solutions that we constructed first to find this maximum amplitude. We found that the ergo region forms. Mm-hmm. Okay, but of course, if you start with some generic thing, in the time-dependent solutions, there's no ergo region.
Yeah,
right?
yeah.
You need a killing field for ergo regions. So the time-dependent solutions don't have ergo regions.
Oh, I see. So then, and then you're saying, so then that means we shouldn't really worry about
So,
that.
so we did worry about it because we worried that that would be sort of taking over what we wanted to show, but in the end, it doesn't seem to be a problem.
Okay, thanks.
Andy?
Yeah, so if we want to talk about cosmic censorship in a semi-classical quantum theory, a Schwarzschild black hole we'd have to define it as the place where the curvature reaches the Planck scale, and a Schwarzschild black hole would evaporate, and that would be a naked singularity.
Sure.
So there's no possibility of a sort of quantum cosmic censorship. That's a simple counterexample.
Right, right.
So it's a classical concept, but now the weak gravity conjecture has an H-bar in it, right?
Well,
So-
it depends on how, basically they want charged particles with charge bigger than their mass. So that,
In
you can say
Planck
that
units.
class.
The charge is dimensionless?
They want extremal black holes to evaporate. And so you can do that classically with, well, no, you can't do it classically.
You can't
but-
do it classically.
Okay, but
So,
you, yeah.
so I don't understand how there's
The H-bar is just the usual thing between a particle and a field. If you think about it as a field, there's no H-bar. Classical charge fields will work.
but it's a charge whose charge is dimensionless, right? So it doesn't make sense to say that it's less than its mass. It has to be less than its mass in some, greater than its mass.
Units in which the extreme of black hole.
Yeah, but the mass isn't really a mass, though. It's the coefficient of phi squared and the Lagrangian. And relate that to a mass involves an h-bar. But we can just call it the coefficient of phi squared and the Lagrangian, and we can compare it to the coefficient of r and the Lagrangian.
Yeah, we did the calculation without any H-bar. So I think
It doesn't just become, the charge is positive because the Planck mass is going to infinity?
No.
Charge is dimensionless, so what is the number that the charge is bigger than?
let's see, what is the number? We can sort it out.
Okay.
But I don't think that's a problem.
Yeah, I mean, Andy, this is
I thought it was a quantum concept, the weak gravity.
parameter in the Reisner-Nordstrom solution. There's a parameter which is 1 for extremal black holes and 0 for Schwarzschild black holes, and that's the parameter he's talking about. We call that the charge in units of the mass somehow, right?
Yeah. Well,
Shiraz?
So in the first part of your talk, perhaps in the older literature, I'd seen these hovering black holes that were alternate stationary solutions.
Right.
So I expected your solutions to pinch off and form the hovering black holes. That never happens.
okay, so Shiraz is pointing out another class of solutions that we found, which are indeed hovering black holes. So in the original Einstein-Maxwell case, there are solutions where you have extremal spherical black holes, ordinary sort of extremal spherical black holes that just sit there hovering above this planar horizon. And they can do that because the normal gravitational attraction to the horizon is balanced by an electrostatic attraction to infinity. Okay, and when we included the hovering black holes, there was no maximum amplitude either. You increase the thing and the hovering black hole just gets bigger. Okay, for the original class of examples, it didn't matter because we were pure Einstein-Maxwell, and you can't form a charged black hole. There's no charged matter fields in Einstein-Maxwell. So we start with ADS, we turn on a Maxwell field, but there's no charge anywhere, so you can't produce any hovering black holes. So that was why it wasn't a problem in the first case. In the second case, with the charged matter field, there's a possibility you produce a hovering black hole, but we already have no violation of cosmic censorship. We could already get to arbitrarily big amplitudes, so that wasn't a problem. In the vacuum case, we have worried about whether there could be hovering black holes, extremal rotating black holes that might save you. But what we find in that case is that the singularity, the region of large curvature, is not on the axis, but it's off the axis, so it's effectively along a ring. It looks like the curvature is getting big along a ring, like the Kerr solution, except outside the horizon. So there's no hovering black hole that's going to shield it, that's going to cover that up. And so I think we're okay without worrying about the hovering black holes.
Oh, follow up, is that okay?
Go ahead.
As you know very well, in ADS, when you have these overspinning black holes which spin at faster than omega greater than 1, these black holes are unstable.
Yeah.
And there's no known endpoint to this instability.
Right.
Would this be an example of cosmic censorship violation?
Yes, so that's another class of possible counterexamples to cosmic censorship, which have been discussed in the literature. In fact, our chair of the session has been working on that recently. Until I talked to him yesterday, I thought that I understood the endpoint. That's a super radiant instability where I thought what was happening was that the energy was being transferred to smaller and smaller scale perturbations, higher and higher sort of azimuthal quantum number modes, and that the likely endpoint of that would be to form, little tiny black holes in ADS. So if that's the case, then it would be a way to violate cosmic censorship, but again, one involving maybe little tiny regions of high curvature, whereas this class of counterexamples might produce much larger regions of high curvature. That would be a difference.
Okay, final question for Avi.
Just a pedagogical question. You showed this table with the number of Amax
Yes.
for different fall-offs.
Yes.
Is it easy to understand where it comes from? Is it related to an energy, an integral of your electric field over the box that defines the anti de Sitter? What sets this number? Can you have a better understanding of it?
We don't. We don't really have an analytic.
But what's the physics behind it?
The physics.
Yeah.
You're getting a lot of electric field lines. You're increasing the strength of the electric field lines. They're self-gravitating. They, in some sense, collapse, I think. They're sort of just getting bunched up so much that they're producing.
Well, so then it may be possible to build a toy model for how that happens.
Maybe, yeah. This is just coming out of the numerics.
All right, let's thank Gary and all of our speakers for today.